Hello students, good afternoon. Our today's topic, nuclear physics. This chapter contributes usually 2 questions in NEET exam. 8 marks. On May 3rd NEET exam, from this chapter, they've given 2 questions. Both are from properties of nucleus only. Both from properties of nucleus they have given. One is they've given nuclear density, mass of nucleus, and they asked mass number. And the other is some statements given, volume of nucleus is proportional to mass number, volume of nucleus is proportional to mass number power 1 by 3, binding energy, mass defect, some statements given. Mass defect is equal to difference between mass of nucleus and the mass of all the nucleons, some statements like that. 2 questions, both are from properties of nucleus are given. This chapter, beauty of this chapter is less syllabus. Syllabus is less. Questions will be direct questions, formula-based questions, or simple concept-based questions. Very easy to score these 8 marks. Less syllabus, time consumption is less. Both for preparation and even in exam also, time consumption less. And if proper preparation is there, this chapter is guaranteed for 8 marks. Such area is this. Easy scoring. And this chapter needs frequently repeated revisions. This chapter needs frequently repeated revisions. In fact, I will tell you one thing. Our modern physics chapters are there now. Dual nature of matter, atoms, nuclear physics, semiconductors physics, semiconductors and logic gates. These 4 chapters need repeated frequent revisions because these all 4 syllabus less, variety of questions less, easy scoring, high scoring, time consumption is less. One more set I will tell you, one more set of 4 chapters, that is units and measurements, wave optics, and EM waves, electromagnetic induction, AC circuits. This is another set of 4 chapters which need repeated frequent revisions. I'll give you one strategy. You do revision in this manner. See, first time when you are appearing for NEET exam, the strategy of preparation is different. And for this re-exam, strategy must be different. Already you had complete preparation. In fact, you have appeared for mock test also on May 3rd, official mock test. Complete preparation is over. Now you should focus on speed, accuracy, these factors. So preparation strategy, revision strategy should be different now. What you do is, suppose you are spending daily 3 hours for physics preparation, for physics revision, assume 3 hours you are spending. In these 3 hours, 1 hour you allot for this set, 1 hour daily. The other 2 hours, what you do is, according to your schedule, the other chapters are there apart from these 8 other chapters like laws of motion, work power energy, rotatory motion, gravitation, oscillations, thermodynamics, current electricity, potential capacitor, wave motion. These chapters are there according to your schedule running now. 2 hours, those chapters you allot for those chapters. Suppose one day, 2 hours, Newton's laws of motion you revise. Another day, 2 hours, work power energy you revise, like this. But every day, 1 hour allot for this units, these 2 units. Again, in this, what you do is, for first unit, half an hour. For second unit, half an hour. Daily you allot. First day, suppose today, dual nature of matter, half an hour you revise. You revise the concepts and solve 15 questions, 10 to 15 questions. Another half an hour, units and measurements, revision of points. And units and measurements, mostly you need to practice more number of problems. Problems based on dimensional analysis, error analysis, and measuring instruments, vernier caliper, screw gauge on them. Practice more problems in units and dimensions. In this chapter, half an hour, some 15 problems you do today. Dual nature of matter, half an hour, this one half an hour. Next day, half an hour atoms, half an hour wave optics and EM waves. Next day, half an hour nuclear physics, half an hour electromagnetic induction. Next day, half an hour semiconductors problems you do, half an hour AC circuits. Concepts you revise 5-10 minutes, concepts you revise, then do 10-15 problems. One cycle over, next again you start. Again, fifth day, half an hour DNM, half an hour units and measurements. Repeat this cycle again another 4 days. Again, third cycle. Like this, for one cycle, to complete one cycle, this 8 chapters, half an hour daily, 4 days you are taking. Suppose 4 cycles, if you complete 4 into 4, 16 days time, you can complete 4 times revision, these 8 chapters daily, 16 days. From today, suppose if you take by June 3rd or 4th, you can complete 4 cycles revision, these 8 chapters. They are easy scoring. See, these 8 chapters, nearly all 8 chapters, including I'm talking around 15 questions we can expect, 15, 16 questions, 60, 64 marks. And easy scoring they are, less time consumption, 16 days, 4 times if you cycles if you complete, perfect revision will be over. Because these chapters need frequent repeated revisions to get speed and accuracy. Remaining 2 hours that according to your running schedule, what other chapters you allot. Like this, you plan this revision program. Do revision like this. Do revision like this. This strategy should be different now. Now, coming to nuclear physics, properties of nucleus. You have to focus on these areas. Properties of nucleus. Properties of nuclear forces. Nuclear forces. Then mass defect, binding energy. Then fission and fusion reactions. These areas to focus more. Properties of nucleus. If a nucleus is expressed like this XZA, what is this Z? Atomic number. Indicates number of protons in the nucleus. A is mass number. Indicates number of protons plus neutrons. Number of protons plus neutrons, mass number. Protons and neutrons are the constituent particles of nucleus now. Means protons and neutrons contribute mass to the nucleus now. That's why their total number is called mass number. And nuclear volume of nucleus is directly proportional to this mass number only. If more nucleons are there, more volume will be there. Volume is 4 by 3 pi r cube proportional to mass number, r proportional to a power 1 by 3. R is some constant into a power 1 by 3. 1.2 into a power 1 by 3 Fermi means 10 to the power of minus 15 meter is called 1 Fermi. These properties, revise these properties. Nuclear density is independent of mass number. Density of nucleus. Mass of nucleus by volume of nucleus. Mass proportional to mass number only means some constant into mass number, total mass of nucleus. Volume also proportional to mass number only, some constant into mass number. That means mass number cancel, density is independent of mass number. All nuclei will have same density. Next, isotopes, isobars, isotones, revise them. Isotope, what is isotope? Oxygen 8 to 16, Oxygen 8 to 17. These are two isotopes of oxygen. They have same atomic number, different mass number. They are isotopes. Like that, isobars will have same mass number, but different atomic numbers. Isobar. Isotones will have same neutron number, same. These properties of nucleus, that is this. Next to properties of nuclear forces. Revise it. Daily revise it. Remember these properties. Nuclear forces. Strong attractive forces are there among these nucleons in a nucleus. These nuclear attractive forces are short range forces. They are not long range forces, they are short range. Next, these forces are charge independent. They are charge independent, means attraction between two protons in a nucleus, attraction between two neutrons, two neutral particles, attraction between neutron and proton, one neutral particle, one charged particle. All same only, all three. These forces are independent of charge. Nuclear attractive forces. They are short range forces. These forces will act up to a maximum distance of 2.5 Fermi only. If the distance between nucleons is more than 2.5 Fermi, these forces vanish. These attractive forces, they act up to this distance only. Short range they are. You know, heavier nuclei, uranium, plutonium, these heavier nuclei are unstable. No? They are radioactive, they are unstable. Why these heavier nuclei are unstable? The reason is these nuclear attractive forces are short range. Coulomb repulsive forces are long range. Coulomb repulsive forces among proton-proton electrostatic repulsion is there. These Coulomb repulsive forces are long-range forces. But nuclear attractive forces are short-range. A nucleon is attracted by, it will interact with only the nearest neighbors, not with all the remaining nucleons in the nucleus. As these attractive forces are short range, heavier nuclei are unstable. And these nuclear attractive forces depend on spin. Spin dependent, these forces between nucleons having parallel spin, means spinning in same direction. Attraction is more, interaction is strong between them. Between two nucleons having anti-parallel spin, this nuclear attraction is weak, less. Like that, depend on spin. And these nuclear attractive forces are not purely central forces. They are not purely central forces. These are all properties of nuclear forces. Revise them. Then fission, fusion, their properties. Now let us come into this. Fission, fusion. Fission, fusion, differences. Fission, splitting of heavier nucleus, no? Fission. Fusion, lighter nuclei combine to form slightly heavier nucleus. Fusion. Why nuclei undergo such reactions to become stable? Heavier unstable nucleus splits into two moderate stable nuclei when bombarded with neutron. Uranium, example, uranium if bombarded with a neutron splits into barium and krypton, releasing 3 neutrons and nearly 200 MeV energy in one fission reaction. Fusion example, 4 hydrogen nuclei combine to form one helium nucleus, releasing 2 positrons, 2 neutrinos, and nearly 26.7 MeV energy. Remember this, during fusion of hydrogen to helium, 2 positrons are released and 2 neutrinos are released. Remember this very important. And energy released in one reaction, one fission reaction, one fusion reaction. In that energy released, if you observe, in one reaction, energy released is more in fission, less in fusion, 26.7 there, 200 here. Okay. Now, mass destruction. In fission reaction, 0.1% of total mass of fuel. Fuel means that fissionable material, uranium or whatever you are taking, that fissionable material. 0.1% of total mass of fuel is converted into energy. In fission, in fusion, 0.7% of mass converted into energy. 0.7% of that fuel, that hydrogen, converted into energy. This. That's why energy per mass, per unit mass, energy released per unit mass is less in fission. Energy released per unit mass energy released per unit mass is more in fusion. Energy per reaction is more in fission. But energy released per unit mass is more in fusion. Nearly 7 times more. The efficiency of converting mass into energy is more in fusion reaction than in fission. These are important points regarding fission, fusion, theoretical points, what I am discussing. Efficiency of converting mass into energy for fusion reaction is nearly 7 times more than fission. To revise these points regarding fission, fusion reactions, revise all these points. Okay? These are all given in your notes. Revise all these points. And in this fusion in stars, enormous amount of energy is released by stars over millions of years. The source of that stellar energy, energy emitted by stars, stellar energy, source of stellar energy is fusion of hydrogen into helium. Fusion of hydrogen into helium. This fusion of hydrogen into helium is taking place in form of two different cycles. You have to remember those cycles also. One is carbon, nitrogen, oxygen cycle. In this carbon, nitrogen, oxygen cycle, what will happen? One carbon nucleus fuses with one hydrogen nucleus to form nitrogen 713 and a gamma ray photon is released. This nitrogen 713 has how many protons? 7 in this. And number of neutrons in this is 6, 13 minus 7. This is rich in protons. Proton number is more than neutrons. Such nucleus in which protons more than neutrons is unstable. So to become stable, what will happen is in this nucleus, one proton in this nucleus disintegrates into one neutron and a positron and a neutrino is emitted. Then what will happen? One proton is converted into neutron in this. Out of 7 protons, one neutron converted into neutron. So neutron number becomes 7. Proton number becomes 6. The total mass number 13 only. That takes place in this. So this nitrogen 713 disintegrates into carbon 613. Carbon 613 emitting a positron and a neutrino. This carbon 613 fuses with another hydrogen nucleus, forming nitrogen 714 and gamma ray photon. Then this nitrogen 714 fuses with another hydrogen nucleus to give oxygen 815 plus gamma ray photon. This oxygen 815 again has 8 protons, 7 neutrons, same thing, proton number more rich in protons, is unstable. Disintegration takes place in this manner. One proton in this nucleus converts into neutron, releasing positron, antiparticle of electron, positron. So this oxygen 815 converts into nitrogen 715, emitting one positron, neutrino. Then last one is this nitrogen 715. By fusing with one hydrogen nucleus, forms helium. And that carbon 612 first reaction, carbon is there now. It is released again. And some energy, gamma ray photon. One second. Nitrogen 715 fuses with one hydrogen, C612, He24, this. This cycle, in this what happened? 1, 2, 3, 4. 4 hydrogen nuclei fused to form this helium. Carbon, nitrogen, oxygen, carbon, nitrogen, oxygen acting like catalyst. So this carbon nitrogen cycle to take place, catalyst is required, catalyst. Another cycle is there, proton-proton cycle. These all, you know this proton-proton cycle. Here in this proton-proton cycle, directly one hydrogen nucleus fuses with another hydrogen nucleus to form deuterium. The deuterium nucleus fuses with another hydrogen nucleus to form He23. and 2He23. I'm not writing completely here. I have to go into problems, so just reminding you. These two fuse to form one helium and two hydrogen nuclei again released. Here one positron released here in this and neutrino. And for this last reaction to take place, two helium-3 isotopes required now. Means the second reaction should take place 2 times in the cycle. For that, again you need 1H2 2 nuclei now. So first one also should take place 2 times. This is complete proton-proton cycle. This proton-proton cycle takes place at less temperature than this carbon-nitrogen cycle. Remember these points. This takes place, this needs less temperature, proton-proton cycle, because these nuclei which are fusing have less positive charge. Here the nuclei which are fusing have high positive charge. More repulsion is there no? Between combining nuclei. As more repulsion is there, they need more kinetic energy to combine. So more temperature is required. Carbon-nitrogen cycle takes place in stars whose temperature is greater than temperature of sun. High temperature stars, carbon-nitrogen cycle. In stars whose temperature is less than the temperature of sun or equal to sun temperature, in those stars, proton-proton cycle takes place. Proton-proton cycle doesn't need any catalyst. But this cycle, carbon, nitrogen, oxygen cycle needs catalyst. This is the difference between these two cycles. Okay? Right. Revise all these points. So these are all theoretical points, important theoretical points. Briefly, I revised to remind you all these points again. Now, coming to problems, see that first problem, see that the binding energy per nucleon of oxygen 16 is 7.97 delta E by A. Binding energy by mass number, average binding energy. This is given as 7.97 million electron volt. For whom? For oxygen 16. So you find the total binding energy. Total binding energy of oxygen 16. 16 into 7.97. Similarly, binding energy per nucleon of oxygen 17 given as 7.75 MeV. So again write total binding energy of oxygen 17. What is total binding energy of oxygen 17? 17 into mass number 17 now. 17 into 7.75. What is the question now? The energy required to remove a neutron from oxygen 17. Oxygen 817 should convert as oxygen 816 by releasing one neutron. For this process, how much energy required is asking that. How much energy required? Energy required in the reaction, it is the total binding energy difference Find the difference of these two total binding energies. Total binding energy of product, total binding energy of reactant. Subtract that. Total binding energy of products minus total binding energy of reactants. This will give you energy release. Total binding energy of product means 16 into 7.97. Product oxygenate 16. This minus 17 into 7.75. That is answer for this. Okay? Simplify that. Let us move into next problem. Complete the reaction, some reaction given. This type of reactions, what you have to do? Both sides atomic number, total atomic number, mass number must be equal. Equate, you will get what should be there in this dash 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 she given there. What is this? Neutron he is giving here N plus uranium 92 235. Fission reaction this is. Barium 56 144 plus dash 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 plus 3 neutrons. So this side mass number first I am doing 1 plus 235 is there. This side 144 plus some X, right? This dash 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 unknown nucleus mass number plus 3 into 1. From this find X. Then that unknown nucleus mass number you will get atomic number 0 plus 92 equal to this 56 plus that unknown nucleus mass number, sorry, atomic number, some y I am writing, plus 0, 3, 0, 56, 92, 36 should be that first option, I think, first option. Find that. Balancing, just balancing both sides, atomic number, mass number, you will get easy problem. This is nuclear physics. I told you now, direct, very easy questions will be there. Next, same type of first problem. Carbon 12, mass given C612. It's mass given. Mass of carbon 12. 12 U, AMU, atomic mass unit given. Mass of carbon 13. 6, 13 isotope. 13.003354 AMU given. Mass of one neutron given. 1.008665 AMU given. What is asking? The required energy to remove neutron from carbon 613. C613 should convert as C612, emitting one neutron. This is parent nucleus. These are daughter nuclei. This is reactant. These are products. Here mass is given. That first problem is binding energies are given. See, I will show you first problem. Here. Binding energy of oxygen 16, binding energy of oxygen 17 given. Energy required to remove the neutron from 17 is asked. In this problem, similar type problem this is, but mass is given here, not binding energy. There what we did, total, not average binding energy, total binding energy of products, total binding energy of reactants we found, and then total binding energy of products minus total binding energy of reactants we calculated. Energy required we got. Here mass is given. So mass defect you have to find. Means add the mass of carbon 12 atom and neutron mass. Those products masses 12, 1.0086. These two masses, add them. You will get total mass of products. And reactant carbon 13 mass is there. Suppose if I add these two, total mass of products if I find, what I am getting 12 plus this, if I write 12 plus this 1.00, 13.008665 AMU I am getting. Now, when masses are given, energy of the reaction is equal to mass defect. First you have to find mass defect. How to find that mass defect? Total mass of products, total mass of reactants, subtract them. Mass defect you will get. Means mass which is converted into energy you will get. After getting this mass defect, mass converted into energy, we are getting that in atomic mass unit. You know, one atomic mass unit, if you destroy, one atomic mass unit means 1.67 into 10 power minus 27 kg. This much mass, if you destroy, how much energy you will get, that you can find using mc square. M in kg you have to substitute 1.67 into 10 power minus 27. C velocity of light 3 into 10 power 8. This if you simplify and convert into electron volt, you will get 1 AMU, energy equivalence of 1 AMU is 931 MeV, million electron volt. One atomic mass unit, a mass equal to 1 AMU is destroyed. Energy released is 931 MeV. So you find mass defect here. Difference of products mass and reactant mass. Find that. That mass defect you multiply with 931. You will get the energy released in the reaction. That is this. Okay. I'm moving into next problem. This is property of nucleus. Nuclear radius of aluminium 1327. Aluminium 1327. The radius of this nucleus is given 3.6 Fermi. One Fermi, how much? One Fermi, unit of distance, 10 power minus 15 meter. This is radius of aluminium 1327. What is the approximate nuclear radius of this nucleus? Mass number 64 given. Very easy. What is that? Radius of nucleus is directly proportional to a power 1 by 3. Just a few minutes back, I told you now. Then R2 by R1 equal to A2 by A1 whole power 1 by 3. R2 equal to R1 into R1 3.6 into A2 64 by A1 27 mass number ऊपर का suffix 27. This lower suffix 29 is atomic number. This 64 mass number A. You will get R2 value whole power 1 by 3. 4.8 you will get, I think. This is 4 by 3, 3, 1.2, 1 into 4. 4.8 you will get. Okay, I'm moving into next problem. See, for nuclei with mass number close to 119 and 238 means binding energy per nucleon is giving. Binding energy per nucleon, average binding energy is given. Delta E by A. I'm writing directly here, okay? Delta E by A. First nucleus mass number 119. Delta E by 119 I'm writing. It is 7.6 MeV. Okay. Then second one I'm writing. Delta E2, let us write. Delta E1, let us write here. 238. This value 8.6 given. So I can find delta E1, total binding energy of this 119 into 7.6. Here I can find delta E2, 238 into 8.6. I can find them the total binding energy. Now see question. Now let us see. If a nucleus of mass number 238 breaks into two nuclei of nearly equal masses, 238 breaking into two nearly equal masses means 119 only now. Means this nucleus of mass number 238 is breaking into two nuclei of mass number 119. What is this? Fission reaction. Fission it is. One nucleus X is there. Its mass number 238. It is breaking into two nuclei whose mass number is 119. Then he is asking, what is the energy, approximate amount of energy released in the process of fission? How much energy released in this? Giving binding energies he is asking. So find the binding energy of products, binding energy of reactant, binding energy of products minus binding energy of reactants. If you find, you will get the energy released in this reaction. This is product. This is only in a product 119. This is reactant. Binding energy of product minus binding energy of reactant. So that you have to write. Here, what is the total binding energy of product? Products total binding energy. Two nuclei are there now. This is energy only for one nucleus I wrote. Two are there. So 2 times of 119 into 7.6. This is total binding energy of products. Their difference you have to find. So here one reaction given, he is asking what is this emitted particle R. Same balancing. X 90 to 236, Y 56, 141 plus Z 36, 92 plus 3R. What is this R is asking? What is that R? So first atomic number Z conservation of Z I am doing. Here 92 equal to 56 plus 36 plus this R is a nucleus whose atomic number is some X. Then let us find this X. 92, 92, 56 plus 36, 92 only, no? So X 0 will get. Atomic number 0 means that should be neutron. Neutron it is. Mass number also I am doing for your satisfaction. 236 equal to 141 plus 92 plus. If this nucleus has, actually here I should write 3x because 3 times I have to do now. If this nucleus has a mass number y, 3y I have to write here. 3y. Two 36 equal to 233 plus 3y. 3y is 3. Y is 1, you'll get. So it's particle of mass number 1, atomic number 0. That is neutron. See, this previous problem, fission problem, one more point I want to discuss with you. Fission. In this fission, if m kg of uranium is undergoing fission, m kg of uranium is undergoing fission, then mass destroyed, mass converted into energy is 0.1% of m. M kg I am taking, observe, kg only, kg. Means 0.1% of this m means how much it is? 0.1 by 100 into m. That is m into 10 power minus 3 kg mass destroyed. Therefore, what is the energy released you want? Here I got mass destroyed in kg. Then energy released, Einstein mass energy equivalence I have to apply. Delta m, m into 10 power minus 3. C square velocity of light 3 into 10 power 8 square na. 9 into 10 power 16 you will get. Then energy released 9m into 10 power 13 joule you will get. If m kg of uranium is undergoing fission, the energy released is 9m into 10 power 13 joule. This, if you want, you can convert into electron volt, divide it by 1.6 into 10 power minus 19. That if you write, it will convert into electron volt also. No? One more thing. In this energy, sometimes they'll express in joule. Sometimes in electron volt, million electron volt. Sometime in kilowatt hour. Remember that. Kilowatt hour, kilo, 10 power 3. Watt means joule per second. Hour means 3600 second. Second cancel. 1 kilowatt hour mean 36 into 10 power 5 joule. Energy is called 1 kilowatt hour, you know. Na? Sometimes they'll ask you to express in kilowatt hour also, sometimes in this. So if m kg of uranium undergoes fission, energy released is 9m into 10 power 13. This. Now in this, number of reactions problems also will be there. Number of fission reactions. What is this number of fission reactions? Mass of uranium is m gram, suppose. Here gram I am taking because mole concept I have to apply now. Gram only you should take in this. Mass of uranium taken for fission reaction is m gram. Now in this m gram uranium, how many uranium atoms are there to find? That many fission reactions take place. Every atom will undergo fission, every nucleus. So how many atoms are there to find? For that, the Avogadro number I have to use. Number of atoms in 235 grams of uranium 235 is 6 into 10 power 23. Avogadro number. The number of atoms in m gram in 235 gram, n atoms are there. In m gram, how many? Mn by 235 will get. Every nucleus will undergo fission. So number of fission reactions. Number of fission reactions is Mn by 235. This M must be in grams only. N is Avogadro number. This is the number of fission reactions taking place if m gram of uranium is undergoing fission. And if energy released if this is if energy released in one fission reaction, if it is 200 MeV, sometimes they'll give energy released in one reaction is 150 MeV, some other value. If it is 200, then total energy released in m gram uranium fission, total energy released is that number of reactions Mn by 235 into energy released per reaction, 200 MeV. This also you can use. To find energy released in fission, two methods are there. 0.1% mass destroyed. Using that, you can find you are getting energy within 9m into 10 to the power of 13 in joules you will get. Here mass should be substituted in kg in this, kg. This is another way. Mn by 235 into 200 MeV. Here in answer in electron volt first you will get. This mass must be substituted in gram. Okay, going to next question. 1 AMU equal to how much energy is asking? 1 AMU in joule is asking 1.67 into 10 power minus 27 kg, 1 AMU. Then energy released mc square 1.67 into 10 power minus 27 into c square 9 into 10 to the power of 16 joule. So many joule. This if you divide with 1.6 into 10 power minus 19, you will get this answer in MeV, 931 MeV, million electron volt. One 1.5 into 10 power something you are getting. Suppose in a question, if they ask, what is the energy equivalence of 2 kg of uranium? Suppose this is asked. What is the energy equivalence of 2 kg of uranium? Means it is not that 2 kg of uranium undergoing fission. Total 2 kg mass destroyed. Then what is the energy released? It is asking. What is the energy released if 2 kg of uranium undergoes fission? If they ask, that is different. Then you will apply this. That 9m into 10 power 13 joule, m 2 kg, you will substitute. That is energy released if 2 kg of uranium undergoes fission. This is not fission. What is the energy equivalence of 2 kg of uranium? What is the energy equivalence of 2 kg of anything? But to mislead you, they use uranium, that word. Anything, any mass, 2 kg mass destroyed. What is the energy release? They are asking. So this question, this Einstein MC square you have to apply. That is 2 kg mass destroyed totally into 9 into 10 power 16. C square value. So many joule. Don't confuse. Just observing uranium, it is fission like that. See, the energy released, that previous calculation one I have shown now. This is that type only. The energy released per fission. Energy released per fission of some nucleus mass number 240 is 200 MeV given. What is the energy released if all the atoms in 120 gram of this substance undergo fission is given? Means what is the mass of that substance used for fission reaction? What is the mass? 120 gram. So in this 120 gram, how many atoms are there? I have to find. In this 120 gram, how many atoms are there? I have to find. How to find using mole concept? When you are using mole concept, the mass must be taken in grams. He gave grams only here. 120 gram. So, what is 1 mole of this element? Mass number 240 given. 240 grams of this element is 1 mole. Means in 240 grams of this element, n atoms are there. 6 into 10 power 23. Avogadro number. So, I am writing like that same steps. Number of atoms in 240 grams is 6 into 10 power 23. Avogadro number. But what I want? Number of atoms in. How many grams? 120 grams I want. How much it is? Half. 120 by 240 into 6 into 10 power 23. 3 into 10 power 23. 3 into 10 power 23 atoms are there. Every atom will undergo fission. Every atom. One fission. So total number of fissions, how much? Total number of fission reactions. How many atoms are there? That many. 3 into 10 power 23. In one fission, what is the energy released? 200 MeV. In this many fissions, what is the energy released? 3 into 10 power 23 into the 200. MEV. 6 into 10 power 25. Into 10 power 25 given 6. Okay, students, all the best. Revise according to that strategy what I gave you. Revise. Who stay calm and have smart revision will have high advantage in this re-exam. Now you need to focus on speed and accuracy. Okay, right. Thank you.